Great time to move on to our next talk. So I'd like you to all welcome Daisy Holman, who is going to tell us about some cute code which we should learn from and never write. Hey Daisy, how are you doing? Oh, you're muted right now. Of course, it wouldn't be a virtual conference without having someone muted when they're not supposed to.
Oh, we did a tech check, and then I muted to just be safe, just in case I was backstage and stuff. But yeah, nice talk. Thank you so much. There was some very interesting things there.
Yeah, thanks. I basically I wrote a big Twitter thread in order to teach myself all of the different features, and then just stuck them into talk involving cats. So. All right. I'm going to hand you all over to Daisy. Take it away.
All right. Are my slides showing up on the screen? I don't see my slides yet. Oh, there they are. Wait, nope. Those are size slides. There we go. All right. So yeah, I'm giving another cute C++ tricks talk. Some of you may have seen my talk back in at CPPCon last year, where I gave kind of part one of this talk. This is part two of this talk. If you're not really familiar with what I'm going for here, basically we're just going to hang out for 30 minutes and have some fun with some weirdnesses of C++. But there is a point to this, and it's really that we want to learn some new things about how C++ works. And it's quite easy to kind of remember these things when we use them in these bizarre ways, right? These things that the kernel of truth in these tricks will come up in real code, but hopefully the way that we're using them here won't actually come up because it's just so bizarre. But hopefully we will get some ideas of how to do the same thing the right way, if it is in fact a thing that you should be doing. And most importantly of all, I think we're going to try and talk a little bit about how do you learn these things, right? How do you play with the language in ways that will enable you to learn new things about the language and have them stick in your mind. As always with this kind of talk, disclaimers: don't use these tricks directly in real code. Don't copy them like you would from Stack Overflow. Don't copy code from Stack Overflow either. That's also a thing. But do use them to learn things that will help you understand existing code. And this is just to basically say the same thing as the first bullet. This is not a software engineering talk. This talk is about surprising snippets of code, and well-written code should be unsurprising. And the definition of unsurprising can definitely depend on your audience. I've presented some of these before and had people say, oh yeah, I use that one all the time. And that's because they're writing for an audience where that code is unsurprising, right? Somebody who writes a compiler or has been working on C++ for years will understand the implications of some of these things maybe better than your general audience. So always, always, always write code that should be unsurprising for your audience. Think about your audience when you write code. I do have a problem in most of my talks of getting too into the weeds. So I've just kind of leaned into it in my last few talks. This talk is all weeds. It's going to get very into the details of what's going on in these snippets and what's interesting about some minutia of C++. It's actually several mini talks. I'm going to kind of jump around depending on how time is going and go through these tricks, trying to leave enough time for questions. So I may skip some of them. I have 3 tricks prepared. I don't think I'll get to all 3. I'm just going to try and fit them in based on time. So anyway, let's jump in and we'll have questions at the end. So here's the first trick. This is, I tweeted about how you can use assert in Constexpr rather than static assert. I think most people who have tried to use static assert in a Constexpr function have kind of looked at it sideways and been like, why isn't this working? This is evaluated at compile time. And so we're going to talk about why that doesn't work the way you think it does. So here's basically the core of the trick. We have this cheesy function that is very simplified A to I, only for unsigned values, that goes through a string and accumulates the value into something to return. We can skip digit separators. The single quote in C++ is a digit separator. So if you didn't know that, that's a thing you could learn from this. And here we need to validate our input somehow. And why not just use assert, right? I mean, the whole goal of Constexpr code looking like it does is that we want it to look like normal code, right? The whole goal behind Constexpr is to have compile time code look like runtime code as much as possible. You might think, oh, if this is only being called at compile time, I should be able to use static assert. And that's actually not the case, and we're going to see why in a second here. So let's step back and say, what does Constexpr mean in C++? This is the committee, and in general the language has a major problem with reusing keywords to mean something different. And Constexpr, static is the most famous case of this. Constexpr is no different, right? Constexpr is at least 3 different keywords, maybe more, depending on how you count. And they all mean very different things that are only tangentially related. And I think, look, in the committee's defense, there is a lot of legacy C++ out there. Every time we introduce a new keyword, we break someone's code because somebody could have used that in their code 20 years ago, and they don't have access to the source code anymore, or they are, have changed things and they have to change too much. So in our defense, we try not to use too many different tokens for things. But I think in this case, we have so many different uses of the keyword that are so distinct that maybe we should have chosen multiple different keywords for it. And I think hopefully I'll convince you of that in the next few slides. But hopefully you'll understand what I mean, at least by that. So yeah, Constexpr depends on which Constexpr you mean. So we have Constexpr variables is one version of that. Constexpr functions is another, where we have Constexpr in front of the function declarator. And we have, as of C++ 17, Constexpr if statements, which we really should have called if Constexpr statements, because if Constexpr statements are, that's the syntax. But we're great at naming, so anyway, if Constexpr statements allow you to do things that in one branch that say some things that wouldn't be legal if the condition wasn't true, right? So and I'm not going to get into the details of that because this isn't about if Constexpr statements, but there's also more. If I have time, I'll come back to this and talk a little bit more. But we're going to focus in on Constexpr functions here. Let's talk about the differences and why I think these are kind of sort of different keywords. So one way to look at the differences here is to look at how what part of the expression or statement does the keyword require to be a constant expression. I'm not going to get into the difference between a constant expression and a core constant expression and an integer constant expression, partially because I don't understand it myself. You'd have to talk to someone who sits in core on the C++ committee, but partially because it's not really important here. I'm just going to loosely use the term constant expression to mean something that can be evaluated at compile time by the compiler. And I'm not going to go any further into technical details of that. But if Constexpr is the other use case, that's pretty straightforward, right? It requires this conditional to be a constant expression, right? But what about Constexpr functions? It's really not clear, right, what they require. Constexpr functions and function templates, you would initially think from these other two that maybe the function body is the part that's required to be a constant expression. And it's not that simple. So let's explore that a little bit more here. So we have, for a function, let's look at how we can use a function that is declared Constexpr. And you're going to see that it's pretty closely related to the other uses of Constexpr, which is probably why it was attractive for us to reuse the keyword, right? We can use a Constexpr function to initialize a variable. So right here you see we're using the function in another place that the keyword is requiring a constant expression, right? Another example is static assert, right? The part inside the parentheses of static assert has to be a constant expression, and we are using our Constexpr function as part of that, right? We can even use it as a non-type template argument, right? This is going to be, you're going to see this less often, but this is a thing that definitely happens and is allowed, right? This is required to be a constant expression, because otherwise how would C++ even form the type? How would it find the definition? How would it find specializations, right? And so that's another place we can use it. But only as long as its arguments are also constant expressions, right? This doesn't make any sense at all. We can't static assert that something we read in from the command line is 42, right? The compiler has no idea what you're going to read in from the command line. So what we did with Constexpr functions to avoid having to write things twice is that we do allow you to use a Constexpr function with runtime parameters as long as it's not in a spot where it's required to be a constant expression, right? And so in this case, since this is just a normal variable, right, and not a Constexpr variable, this just works fine, right? And you're probably used to this, right, in C++. Whether or not you're aware of it, a lot of the standard library is Constexpr, and you use it in runtime code all the time. So what do I mean by Constexpr means maybe this might be evaluated in a constant expression, right? That's what I put in the original tweet. And I think is really the kernel of learning that I'm trying to get to in this example, right? And so according to the standard, a Constexpr function that can never be used in a constant expression is ill-formed, right? Anytime we would try to use increment foo in a constant expression, like a static assert, like the right-hand side of a Constexpr variable initializer, the function is the program is ill-formed, right? We cannot. This function never produces a constant expression, and compilers will diagnose this sometimes. I'm getting to that, but if you put this into Clang, you'll get a error that a Constexpr function never produces a constant expression. But then you have this thing in square brackets that tells you something else weird is going on. -w invalid Constexpr, which is W is not usually used for errors. It's usually used for warnings because, warnings start with W. And so you're like, why is this? Well, take another example that's just slightly more complicated, right? And we have a function calling another function, this f with no arguments, calling this f with an argument. This example actually comes directly from the C++ standard, by the way. Some of the examples in the C++ standard are quite helpful, and I think many of them are, actually. We spend a lot of time crafting those examples as we write the standard, but we're not really writing it as a tutorial. We're writing it for compiler authors. But anyway, this first function is totally fine, right? It can be called in a way that would produce a constant expression, right? If we call this with false, it returns 0. That's something the compiler can do at compile time. But if we call it with true, it throws an uncaught exception, right? Which cannot be done at compile time. So because this second function unconditionally calls the first one with true, the second function can never be called, can never be used in a constant expression, right? Never produces a constant expression. And the standard says this is ill-formed, no diagnostic required, which is terrifying and a big problem. And actually, we're working on fixing that in this particular case. But it means that this program compiles fine, which means that this Constexpr here literally does nothing. So I guess that's the fourth meaning of Constexpr. It's nothing. It makes your program ill-formed, but that doesn't really have any real-world consequences because, this we never try to evaluate this at compile time. If we ever tried to evaluate this at compile time, we'd get an error, right? Because the compiler can't evaluate and can't throw at compile time and not catch, right? Function templates work the same way, basically. All we have to do is add this template parameter to confuse the compiler enough to compile this, even though there's no way we could instantiate. There's no template parameter for which we could instantiate this, right? That would cause this to be a constant expression, right? So why is this ifndr? ifndr meaning ill-formed, no diagnostic required. And it's because we don't want to force compilers to solve hard problems, right? This is kind of an inverse problem where the compiler has to figure out all of the possible inputs. Now, for bool, it's obviously pretty simple, but if this were an int, right, then how does the compiler know without kind of exhaustively trying that, all of the integers it's tried so far, like 1 through 42, don't produce constant expressions, but maybe 43 does, right? So we don't want to force compilers to solve these inverse problems, and so we made this ifndr in the standard. That might be changing. I'll get to that in a bit. But basically, this is the summary of how ifndr is treated by compilers. The world's blowing up around them, and the compiler is just happy and oblivious and just lets it go. So let's get back to the original tweet. Why are we allowed to use assert in a Constexpr function? So if we look at this function that we just dissected, right, from the standard that the standard says is okay, right? We can actually call this, as long as we're calling it with false, we can put this in any of the places that it's required to be a constant expression, right? We can static assert with it. We can even initialize a type with it. And this to me is profoundly weird, right? Because if we had called this with true, this whole program wouldn't work, right? We're not really used to runtime looking parameters determining where we can call a function. But this is how C++ works, and that was something that was very surprising to me and that I learned from this. So if we look at how the assert macro is usually defined, it basically looks like this, actually, right? It's turns your thing into a bool, and if your assertion is true, it just returns 0, right? It's fine. Otherwise, it calls this function assert fail, which is hopefully pretty obviously not Constexpr, right? You can't assert fail. That's a runtime symbol. So assert expression is only a constant expression if expr evaluates to true. But that's exactly what we want, right? We want constant evaluated code to not compile if the assertion fails. And the diagnostic for this used to be horrific. It used to be like you never actually could tell that the reason why your code wasn't a constant expression was because of the assertion. It has gotten a lot better in the past, like literally year. Clang now basically says, your assertion failed and that's why this isn't a constant expression, which is pretty useful. We are working on the IFNDR. I don't have time to get into this more, but read this paper by Barry, or tweet Constexpr questions to Barry. He loves to talk about Constexpr and things like this. He can probably explain to you what a core constant expression is and why it's called a core constant expression and not an integer constant expression. Yeah. I'm going to move on. I think I'm going to skip. I didn't mean to exit full screen. I think I'm going to skip my second trick and dive into my third trick because I like that one more. I'm sorry I didn't get to the second one. I'll have to do it in another talk. This one, and I'm running out of time. This one has a lot of really interesting nuggets to it, and I thought it was mix in some good variety because it's a little bit more advanced than my first one. So I tweeted this around Halloween, I think, and that's why I said spooky. But this is essentially the text of the trick. The main thing I want to focus on in this slide, and I'll go through the rest in a second, is that we're creating this like global registry looking thing where we can call set with a template parameter, and then when we call get with the template parameter later, we get it back, and then when we can call set again, and then when we call get again, we get the thing that we set back, right? So we're kind of like, and this is cute, right? This is you can imagine a number of right ways to do this. I'm going to show you a very, very wrong way, but there's an interesting kernel of truth in here to learn about how lambda capture works. And I really want to get to that if I can, so stick with me. So here's a very simplified version of, not very simplified, but slightly simplified version of this trick. We've taken away the template parameters for a second because it's a lot less catchy this way, but this will explain basically the same thing. And I'm also throwing 0 instead of throwing success because I thought throw success was hilarious when I made the trick. But just to save some space and thinking. So what's going on here? Well, we have a set function that calls this impl function that's used by both get and set. And it calls it with its argument and then catches any ints that are thrown out of it and just ignores them, right? And we have in our impl function, right, when we call it with an argument, it stores the argument v, right, in a static variable that while it's initializing, the storage happens while it's initializing another static variable. And then still in the initializer of that other static variable, we throw and don't catch it, right? So anytime we have an uncaught exception, right, we exit the current scope, right, and the function ends, right? So this line here is very clearly unreachable. I used a comma operator here for compactness, but really we could do this as an immediately evaluated lambda also, where we, say stored equals v and then throw, and then this line is clearly unreachable, but it still needs to be there in order to make this function properly return 0, right? It has to still have a return type. Properly return an int. So it still has to have a return type, right? And we're going to see that later in a second, that we have an unreachable return statement that's still determining the return type of the function. So what happens when a static block local initializer throws? I went into much more detail on how this all works in my CPPCon talk. I don't have time for it now, but basically C++ guarantees that these initializers will run exclusively by the first thread that gets there, and then the next threads will wait, right? If the initializer fails, then the next thread will try it, and the next thread will try it, and the next thread will try it until the initializer succeeds without an exception, right? Runs to completion without an exception. Since this one never runs to completion without an exception, just every thread that reaches here will run this statement and then get out of here, right? This runs with exclusive access to stored, because C++ guarantees static initializers don't race with each other, right, for a given static initializer. It also will always run because it never completes without an exception, right? And that's just summarizing what I just said. How are we getting the value back, though? That's the kernel of truth in this that's really interesting. So line 4 is clearly unreachable because line 3 always throws, right? We've established that. But line 5 still determines the type of the function, right? The function still returns a lambda of that type. The type of every lambda is unique, right? That's how lambdas work in C++. It's a unique generated type in the compiler that we can't write the name of. But we can write the name of using decal type, right? We can say, this thing that you made up, right, compiler, I want to name that type. And if it doesn't capture anything, it's guaranteed to be default constructible, right? And we can just construct it, right? So here we've constructed that lambda that is returned there without actually ever having an instance of it. So we don't need to return it to make an instance. We just default constructed it. And because it doesn't capture anything, every instance of that lambda is equivalent, right? Static variables are not part of the lambda capture, right? This stored here is actually, notice that we're not capturing anything, right? This stored here is actually built, it's baked into the type and not any particular instance, right? So every lambda that captures, every lambda is a different type anyway, right? But the reference to this static variable is part of the type, not part of any particular value associated with that lambda, right? So we are able to, just by reconstructing another instance of the type, we are able to get access to stored without ever running line 5. And then if we just call that lambda, we get back the static variable spookily, right, without ever executing line 5. The rest of the trick I don't have time to get into because I want to save time for questions, but basically we're using template parameters as keys, and we can do that because every instance of a function template with different template parameters is different, and thus every lambda inside of it is a different type, and so we can reconstruct a different type pretty easily. And I will take questions now. Thanks for listening. If you don't get time to ask your questions or you think of one later, feel free to tweet them at me or email me, and I'll try and get back to you on them. Thank you so much. Are there any questions? I think I went over time a little bit, so hopefully that was understandable. Looks like Sai is going to come back in a second.
Hey,
Hi,
thanks
Sai.
very much for the talk. Oh
Yeah,
god, that second example is horrifying.
it is horrifying, isn't it? I forgot to say, credit goes to Richard Smith for that. One of the cool things about working at Google, is that I get to work with people like Richard Smith, who were just absolutely brilliant, and like C++ wouldn't exist in its current form without him. And he came up with that, and I kind of just polished it into something that would catch people's eye on Twitter. Yeah, it's but the interesting thing about that example to me is that understanding how lambda capture works with respect to static variables is actually very important. It actually I can't name specifics, but there was a project at a previous place of employment that we worked with that literally specific mistake or mistaken understanding cost them significant amounts of money because things weren't transferring to the GPU correctly because the capture didn't work the way they thought it did. That's even if you give a default equals capture, right? There's no actual copy of a static variable. It's baked into the type, and so if that instance is on the CPU, then and you send the lambda to the GPU, you're not actually going to get it, right?
Yeah, for sure. Yeah, I like the
And
way
that actually costs a lot of money.
I like the way you talked about Constexpr in the first part as well. Like, I always had the intuition that there's the different uses of Constexpr can sometimes mean wildly different things, but having it so clearly laid out is very useful.
Yeah. I wish I had gotten time to go into constinit and constival, because I think those are actually, we did the right thing there, right? We had two different keywords and we named them two different things. And they're pretty closely related to what we did. But yeah. Thank you so much for the opportunity.
Thank you so much
speak.
for coming along. Yeah. And that says it time for this session. So everyone say bye to Daisy.